So probably one of the most important jobs that you do as an analytical chemist is the quantitation piece. Without the quantitation piece, you can't answer the how sure are you piece. Right? So there's qualitative analysis where you learn what it is, but a quick database search might tell somebody that. You run the sample and it does a hit list, and you've got the top hit and it's 99% match. Then that's pretty easy. Someone with a very low level of education could do that. Maybe someone out of high school that's trained to put the sample on and then run it against a search library. But the quantitation piece, the skills in quantitative analysis are much more detailed. And so this is where you are really required to use your degree. And so let's talk about predictive modeling and calibration. So there's some terms that we will use in here are the dependent variable versus the independent variable. The x-axis typically is the independent variable, that's the concentration, and then the signal depends upon the concentration. So the dependent variable is the signal that you're getting. Some other things are linear dynamic range, and we'll talk about the linear range of a calibration in orders of magnitude. So this is I first remember hearing the term orders of magnitude in physics. So they were talking about sort of sizes in orders of magnitude, or an estimate. If you were to estimate a value, you could at least estimate to the right place value. So place value is another word for order of magnitude. You're in the hundreds or thousands or millions. And so the linear dynamic range in order of magnitude means you can take something, let's say concentrations, give you signal that go from, say, 0.1 absorbance value up to, say, 5 absorbance values. And so that's not a very big range. In orders of magnitude, that's just 2 orders of magnitude. 0.5, so that's the 10th place, up to 5, which is the ones place. And so your signal has really only got 2 orders of magnitude, whereas peak areas on a gas chromatograph, they can see small peak areas, which might be in the thousands, up to enormous peak areas, which might be in the millions. Okay, so there, going from 1,000 to million, you've got 3 or 4, depending on if you count the 1 or not, you've got 4 orders of magnitude. And if it's linear across that whole range, then that's what we're talking about. The linear dynamic range of your calibration may go from 1,000 to 1,000,000. And that's great, because that's going to cover a large range of concentrations. If your signal varies that much, and your concentrations are going to be varying quite a bit as well. What this allows you to do is to analyze samples that are very concentrated and samples that are not very concentrated, and to do that in a linear fit. So this linear dynamic range is a measurement of your instrument's ability to measure the ranges of concentrations. Then we have the limit of quantitation. This is the smallest significant concentration in the linear dynamic range. And we'll see a plot here in a second with all of these on the plot. So when I say significant concentration, this means you're statistically confident that you're giving it a number, right? And then the limit of detection is just the smallest significant signal. Notice the significant things are different in these. In the limit of quantitation, it's the significant concentration. You're actually assigning a concentration. But in the limit of detection, you're not able to quantify it. You're just saying, yeah, I've got a real signal here, but it's not up in my linear range, and so I'm not going to make the claim that I know how concentrated it is. And then your correlation coefficient, we talked about this already. That's the percentage of your data that is captured by your model. So your data has a certain amount of scatter in it. What's the percentage of the scatter in that data that's captured by your model? Then these other terms are all defined. I'll find that page 70 and I'll print that off and put that into Blackboard. But controls are known samples that you're running through your calibration just to check your calibration. So that's why it's a control sample. And blind controls are ones that someone else prepares and they know the concentration, but you don't. So you can check your number bias. In that case, you have no idea where this one should show up. Calibration checks, again, you can run one of your calibration samples again. replicates running the same sample through the, multiple times, and duplicates are samples prepared in an identical way. And then spikes, you can take a sample and spike it with more analyte. And so you've got a sample that comes in maybe low on your dynamic range, but you spike it with a little bit more, and it puts it up into the middle of your dynamic range. So here's a horrible calibration curve, because look how scattered the data is. But this is the one that came from the Bell book. And so that linear dynamic range is shown in the middle. The order of magnitude would be the number of place values covered by this range here. So like if this is 0.1 up to 100, then that's 4 orders of magnitude. Everybody follow that? Yeah. So how many place values are in the linear range is your orders of magnitude for your linear dynamic range. Now, almost every instrument is going to saturate at some point. So even peak area in a GC, eventually the signal gets too tall for the detector and starts to flatten out. And that doesn't mean that there's not signal there. You're just not able to count it. You're not able to capture it. And so you're missing some area. So at this really high concentration over here, the peak area is being clipped. And so the signal's not as high as it should be. It should be way up here, but it's not. It's actually right there because it's being clipped. And so anytime you see even a spectroscopic measurement where the peak's coming up and it starts to flatten out at the top and then it goes back down, like somebody just chopped the top of the peak off, that is saturation. It's like your detector can't see any more sample. So really strong samples will saturate your detector. And your detector, it could be a chromatograph, it could be a spectrometer. All of those instruments are going to saturate. If it's an electrical measurement, there's going to be a max voltage that it can measure or a max current. And it's going to hit that maximum. And so what do you do in that situation? Well, you can take this sample and cut it in half. And then it'll show up here and it'll be right in the middle of your dynamic range. And so if you run a sample, you start to see saturation, then you come back, you cut those samples in half, do a dilution, and run them again. And you can then get them down into your dynamic range. At the lower end of your dynamic range is your limit of quantitation. And so you're quantifying it, and so with your quantification, you're also providing some uncertainty with that. And so you're saying that you're confident that it is this value, but you are down at your limit. Okay, so you're less certain about your limits. The uncertainty, if you were to look at the uncertainty for your dynamic range, I'm gonna plot it here. It will look something like this. This is kind of like what I would call your error bars. And so this one here has got error in the Y value there and the X value here, okay? So a concentration here would have an uncertainty in signal that's that tall, or a measurement of signal would have an uncertainty that's this wide in concentration. You see why this is such a crappy calibration curve? Because the data is scattered all over the place. Okay. But look down here at your limit of quantitation. If you get a signal here, right there at your limit of quantitation, this is the maximum concentration it could be. This is what you think it is. But look, the negative error bar kind of goes off to infinity. So it really might be zero concentration, and you just have a spurious signal that brought it up into your linear dynamic range. Okay. So this, again, like I said, this is a horrible calibration curve. And I say it's horrible because you draw a linear fit to these data points, and none of these points are on the line. Okay, so there's way too much scatter in the data. So you would go back and redo your calibration samples. I want to pause here. If there are any things you want clarified, now's the time, please. Remember, stickers are on the line too. If you made a pretty good point, and I go, you surprised me with that. Get a sticker. Okay, seeing no comments, we'll move on. Okay, this is again just pointing out the error on the page 65 of the book that they have r squared equals -1, and you're not going to get r squared to be a negative number. There are no imaginary correlation coefficients, and so they're just talking about correlation. Correlation can be negative, but that's like the Pearson correlation constant. This is that would still be an r squared of 1, even if it's a negative correlation. It'd be an r squared of 1. Okay. Oh, here's another thing too. If you wanted to do your own statistics, and there's some examples when you may. There's some. I have had to do it myself, not using any of the trend lines or ANOVA or Minitab. If you're curious about when you would want to calculate your own M and B and R squared values, we can talk about that. It comes in handy sometimes when you can just do it yourself in Excel. Here are the equations for those. Okay, so the sums of squares, so the sum of the squares for XX, that's the sum of all of the X values squared minus the sum of all the X values. You sum it first and then you square it divided by N. So that's why it's called the sum of squares. You square the values and add them together, or you then add all the values and then square the result, divide by N, and it's the difference between those things. And that's S subscript XX. You could change the Y, values, Y, and make SYY. And so that would be the same way you would do for SYY. And that shows up here, SYY, in the R squared value calculation. And then SXY is the X value times the Y value on each row. Like if you had this in a table, it'd be the X times the Y added together. And then that's equal, then you subtract the sum of all the X column times the sum of all the Y column divided by N. And that would be the SXY value. Once you calculate these values, SXX, YY, and XY, then the ratio of SXY to SXX is M. So it's pretty simple to do. Okay, and back in the day, we did this for like 3 or 4 data points by hand, with our calculator. And that's always fun to do, but it's tedious. And then B, once you have M, then you can take the average X and the average Y and M, and you can compute B. And then we've got the equations for all of the uncertainties in B, uncertainties in M, that I can provide you. They're on Blackboard. Okay. So let's look at this calibration example. And this will start, there's 3 calibrations that we'll go through. And we're not going to get through all 3 today. Yes?
Yes, for the previous slide,
Yes.
I'm wondering, why is it that we have to take the average of Y and X in that example for the last equation?
For B, finding B, I'm not exactly sure why. Okay, I just put the equations in here, but I haven't really analyzed why B would be given by the average X and the average Y. But I mean, it's just,
I've never really studied correlation between that and that, because you see how you have Y equal X plus B, and then there's the bar. I was trying to see where did.
Well, I think, what are the other options for finding B? You could find a B using any one of the XY data pairs, but if you have 10 data points, you're going to have 10 values of B. Right? So what do you use to find B? It would make sense then to just use the average X and the average Y to find B. So you're kind of finding the average B, if you will, because you found M using the changes in X and Y using the sum of squares. So, I mean, that may be just like a practical answer. There may be a more deep statistical answer to give, but I don't know. Yeah. That's good. I think that's a good question. You stumped me, so I'll give you a sticker. You get to pick. There's 4 types. You can put it on your notebook. All right, very good. All right. So let's look at these calibration examples. So this is the scenario. You have 125 parts per billion cocaine in blood. So you've taken whole blood, you've put in 125 parts per billion concentration of cocaine and then analyzed it. So the first method is external standards. So we've taken our instrument and we've made standards of cocaine, and we've put small amounts and large amounts, made an external calibration curve, and then we take our 125 parts per billion cocaine in blood and analyze it against that calibration. So this is the traditional calibration that you're thinking of. You make your standards up, get the signal, then put in the unknown, and you get a result. Then we have internal standards, okay, where now a different standard is added to the analysis samples to provide a stable ratio signal. Okay, so we want to analyze cocaine, but we think something may be interfering with our signal. Like we put in 125 parts per billion, but we only detect, say, 90. And we do that every time. So we're like, Or maybe our uncertainty is related to injection differences. So this is really a problem with GC or LC, but mostly GC. When you're having to inject the sample, do you do it exactly the same way every time? Because what happens in a GC? The sample goes on to a really hot inlet. Okay, this piece of glass that's at, say, 200 degrees. And it vaporizes instantly. But is it instant? It's not exactly instant. It depends very much on how fast you push the plunger down. If you push the plunger down slowly and this first amount evaporates and kind of cools the inlet down because it evaporated and used up some of its thermal energy, and then the next sample comes on and it doesn't evaporate as slowly, what that's going to do is give you peaks that tail. It's going to give you peaks that tail to slower retention because you're coming off that inlet a little differently than if you put it in quickly. So on 2 samples, you put it in really quickly, and the 3rd sample, you put it in a little slower, and then the 4th sample was quick again. You have injector to injector variability. And that can cause your calibration curve to have a lot of noise in it. So what you can do is put in an external or an internal standard in there and take the ratio. So you put the same internal standard in all of the samples. And so the only thing that varies is your cocaine. But when you put in a slow injection versus a fast injection, your internal standard will go slow or fast. Will show up at different amounts. And so this internal standard corrects for injector to injector variability because it should be the same across the board. So every measurement should have the same amount of internal standard and differ in the amount of cocaine. And so if you wanted to scale it by the amount of internal standard, you would just take ratios. Take the ratio of the cocaine signal to the internal standard signal. So that's the major difference between the external standard and the internal standard. The internal standard uses ratios, and that's shown right here. So whenever you need to remember that, the internal standard provides a stable ratio signal. So you're actually plotting the ratio signal, not the cocaine signal. And in both of these cases, our standards were made up in the lab with the solvent. So let's say acetonitrile, but our unknown was blood. So that might be a problem with a matrix. Blood's different than acetonitrile. Okay? And so standard additions is where you take the blood sample and you actually add the standards to the blood sample. And so that would be adding standards into the blood sample. Yes?
So the external standard is where you can kind of compare, like, let's say it's at 50 grams per something, and then everything else you can compare against to say it's higher or lower than 50 grams by this amount. And then internal standard is where you can correct for the injector to injector.
Yes.
So then technically, wouldn't it be better to have both external and internal standard at the same time?
Well, for the internal standard, you are kind of combining them. You do have the cocaine, differing amounts of cocaine in the different samples, but you have the same amount of internal standard in each. So you still do have the sort of externally prepped cocaine samples, and then you just add in to each one of those. Let's say you have 10 parts per billion, 50 parts per billion, and 100 parts per billion, you add in, say, 3 parts per billion internal standard to all 3 of those. And so then you take the ratio of the 10 parts per billion signal and divide it by the 3 parts per billion internal standard, and you get this ratio. And then you do that for the next one, it's 10 divided by 3, and the next one's 100 divided by 3. Whatever the signal comes from all of those. It'll be peak areas, and so there'll be huge numbers.
So there are known concentrations of countries.
Yes, known concentrations in each standard and known concentrations of the internal standard.
Mm-hmm.
So it really, really cleans up the statistics, and we'll see that result in our ANOVA tables. Okay, so then anything left about the sample matrix. The standard additions, the one negative on that one is you actually have to have a fairly large amount of your unknown sample, because you've got to take your blood sample and now divide it into 4 or 5 different aliquots that you're going to add standards to. So you take your blood sample that contains 125 parts per billion cocaine, and then you add to it more cocaine. Okay? So you break it into 4 pieces, and the first one you don't add any cocaine, and the second one you add, say, the 10 parts per billion, and then 50 parts per billion and 100 parts per billion. And so we have 4 samples now with 0, 10, 50, and 100 that have been added to the blood. Okay. And you're like, well, aren't you screwing things up? Well, we'll see how it works out. So you kind of backtrack and see how much was there originally. So it's a fantastic analysis technique, but you need a fairly large unknown. Okay. It would work for whole blood, probably. It would work for urine. Probably not going to work for vitreous humor. So you got 1.5 mils of fluid out of the eye, and maybe you could break that into 500 microliter, standards, and then add in your external piece. But it would be tricky to do something with that small of an unknown. So let's go do the external standards, and we'll probably get through the external standards example, and then the class will be over, and we'll do standard additions Tuesday, and then internal standard on Tuesday, and then we'll analyze all 3 at the end with a discussion. So this is the first calibration method you learned in quant. I'm sure of it. And then this system must have, for it to be valid, must have minimal matrix effects. Already, we're going to probably know that we have trouble. We're building our external standards in solvents in the lab, and our unknown is blood. So we've got a totally different matrix. Blood is aqueous, full of salts, and our lab standards are probably acetonitrile, a good solvent for many organic molecules. And so we've got 2 different matrices. So the external standards are in various amounts of cocaine in an organic solvent. Organic solvents are not blood, so this will probably pose some problems, and we'll see what those problems look like. So here's our data up here on the left. I know it's kind of small to see, but we have our external standards in parts per billion, 20, 50, 100, 250, and 500. And these are the peak areas. It's beautifully linear. You see that? This is our calibration curve. Our R squared is 9994, so we have, we captured 99.94% of the scatter in our data. It's gorgeous. Really happy with that. Although some labs will say they must have 4 nines or they've got to redo it. So it just depends on how insane your lab manager is. They say, no, if you don't have 4 nines, we got to redo your standards and everything. So I'd be happy with this. So we can look at this and say, we really haven't characterized our full linear range. We haven't seen where the instrument starts to saturate, and we haven't really gotten down to our blank noises and so on. But even this, we can look to see our lowest one is at 9,000, and our highest one's 200,000. So we certainly have 3 orders of magnitude in this calibration. Could you answer that question if I asked you, how many orders of magnitude signal do you have in this calibration? Just look at how many place values you have that are different. The lowest place value is the thousands, and the highest place value is the 100,000s. So our calibration, if you just look at this, it's actually 3. Did I say 4? So it's 3 orders of magnitude. Three OM. And so we don't just stick with the trend line. We've got to do the full linear regression to get the ANOVA table. So we take this and in Excel, we can put this in as the X values. These are the independent variables, X values and Y values. Or X input and Y input, I think they call it in the data analysis. X and Y input. Run the linear regression, we get the same R squared value, which is satisfying. And then down here we have our coefficients. And our intercept comes in at 1213, and our parts per billion comes in at 417. But look at our standard error. That's kind of a strange thing. Our intercept, we're saying, is 1200 plus or minus 1500. That should raise alarm bells. And of course, now you know you're trying to look at the p-values. And so what's the probability that this intercept was caused by random variation in our data or noise? Is the p-value is 0.47. So it's almost a 50% chance that this intercept is not statistically significant. Yeah. So what do we do in this case? We've got a value in our regression that's not defensible in court or even in discussions with your manager. Yeah, but what are our options if we run it again? We could start over with all our samples and everything, but what this is saying is it's saying B is not statistically different than 0. Okay, so that's the other option. If it is statistically significant than 0, you say B is statistically different than 0. But if it's not statistically supported, then just set it to 0. So this, if you'll notice, you say, well, how can 1200 be no different than 0? Well, look at the slope. It's 400, and look at the linear dynamic range. I mean, it goes up to 250,000. And so these are values way up to 250,000, and then the next value is, or 210,000, the next is 100,000, then 45,000, 21,000. It gets down to 0. You can imagine that would have some uncertainty as to 1200. I mean, our range is so huge that 1200 may not be any different than 0. And so we could redo this and essentially pin this data point down here at 0 and say 0 concentration should give 0 signal. And so we're going to set the intercept at 0 and redo the regression. We don't have to redo the whole analysis. We just have to redo the regression and tell it not to calculate B. We're going to pin it to 0. And that's one of the check boxes in the regression analysis. When you go in there, you select the X input, you select the Y input. There's a checkbox that says set intercept to 0. We would check that and redo the regression. And so here are your values, just showing you all the animations that show that, this is our X input, Y input, B and M. This is SB and SM. You see SB is greater than B, so that's a real problem, the p-value. And so we said that, H0 is that B is insignificantly different than 0, and in this case we keep H0. So here are the formulas for calculating SB and SM. I put those in there. They're on Blackboard, but they're also right here in the notes. And so this checkbox for our Y, just for our trend line, you can come in here and edit that trend line. And here's the checkbox: set intercept to 0. And so notice it went from 416x, so M was 416. When we included 0, now it's changed to 420. But B's not up there because we're setting B to 0. And then we redo the analysis, the ANOVA, with that checkbox, and we get these NAs. That means not applicable. So we're not calculating any statistics on our intercept because we pinned it to 0. And then we just get the slope. And now our p-value for the slope is fantastic. It's 4 4 times 10 to the minus 8. And you can imagine, it's like, what is the chance that random noise gave us these values up at 210,000, right? So there's a 10 to the minus 8 chance that the noise in our data gave us that data point way up at 210,000 and all the ones in between. So now that we have a good model, we can do the quantitation part. So you don't have any business using y equals mx plus b until you get a m and a b that are statistically valid. That's the take-home point. You got to have statistically valid m and b for you to use this model. So we got rid of b because it wasn't statistically valid, so we keep m, and then we use that to calculate our blood samples. So we come in with a check sample. This is our blood signal from blood. And it was supposed to be 125 parts per billion in blood. We run it on our calibration curve. Our signal comes in at 28,000, which 28,000 divided by 420 would give us our 68 parts per billion. It's really low. So this is our sample that came in at 68 parts per billion measured. And our uncertainty calculated from our calibration. So doing the uncertainty analysis, the propagation of error, it comes in at 0.6 parts per billion. So we're pretty sure about that number, right? How much is there? 68 parts per billion. How sure are you? Plus or minus 0.6. If I just use plus or minus the standard deviation, okay. And so I'm pretty sure, but I'm wrong, right? The percent error, I'm 45% low. That's bad. I have a statistically defensible answer, right? I'm pretty sure that my number is 68, but I'm off by 45%. Okay. And so this should, make you think, how can we fix this? And so Tuesday we'll go through the other 2 calibration methods, and we'll see it really matters which calibration method you use to quantify your data. Okay, something could be happening in the blood that's not happening in the organic solvent. And so one of the major things that happens in blood, what do you think is in blood? It's not just buffers. It's not just red blood cells to carry oxygen. What were you going to say? Water. There's water in there. It's an aqueous suspension of all of these things. But one of the things that's in blood is enzymes. And enzymes metabolize things. And you have metabolic action happening on the cocaine. So when you add in 125 parts per billion to the blood, one of the things that starts happening immediately is these metabolism enzymes start to chew it up. And that's not happening in your external standards. You put it in organic solvent, there are no enzymes in there. They're not messing with the cocaine. And so that's a substantial difference that we would call a matrix effect. Okay. Blood has a active matrix. It actually is taking away your signal, whereas organic solvent doesn't. So that's the answer. But how do we account for it in our calibration? And so we'll learn about that next time.